All right, next up we have Lewis structures for molecules and polyatomic ions. So anything that has covalent bonds, we can draw a Lewis structure for. So that means both molecules and polyatomic ions. So make sure to add that to your notes. All right, start off with the octet rule. Oct means 8. Octet rule, many atoms tend to bond in such a way so as to have 8 valence electrons. And so anytime we're drawing a Lewis structure, we need to make sure that each atom in that Lewis structure satisfies the octet rule, unless it is one of the exceptions, and we'll get to those in just a bit. All right, so here are the rules, or rather, I think better word is steps for drawing the Lewis structure for a molecule or polyatomic ion. Step number 1, determine the total number of valence electrons for all of the atoms in the molecule or ion. So you just got to add them all up. If the particle is a negative polyatomic ion, then you're going to add 1 electron for each negative charge to the total. So if the polyatomic ion has a negative charge, that means that it has more electrons than protons. So we're going to add to the total. Particle is a positive polyatomic ion. First of all, why is it positive? That means it has more protons than electrons, or less electrons than protons. If you remember that, that'll help you to remember to subtract 1 electron for each positive charge from the total. All right, next we're going to draw the skeletal structure, it's called. The skeletal structure shows all of the atoms in that molecule or polyatomic ion and how they are bonded to each other. So the first atom listed in the formula of a polyatomic ion or molecule is usually the central atom. Central, or everything else is attached. An exception to this is that hydrogen can never be the central atom in a molecule, or in a Lewis structure rather. Why not? Hydrogen is stable when it forms 1 covalent bond. It wants not 8 valence electrons. It's stable with just 2 valence electrons. And again, it can achieve that by forming 1 covalent bond. So it can never be the central atom. Each line drawn in a Lewis structure represents a shared pair of electrons, aka a covalent bond. So we're going to use lines to represent the covalent bonds between atoms in a molecule or polyatomic ion. Now I'm going to do it a little bit differently, but we'll just fill in the notes here. So next it says to complete the octet of all of the atoms that are attached to or bonded to the central atom. There's an exception to this, again, is hydrogen. Hydrogen never gets any lone pairs of electrons. So everything else we want to complete the octet for the bonded atoms. Next, place any additional electrons on the central atom in pairs. These are called lone pairs of electrons. Number 5, if the central atom has less than an octet, if you've placed all the electrons, all of the valence electrons, and you see that the central atom is short of an octet, then it may be necessary to make multiple bonds. By multiple, we mean double or triple bonds, so that the central atom has at least an octet. Now, there are some exceptions for atoms that when they are the central atom that are stable with less than an octet of electrons, stable with less than 8 valence electrons. One of them is beryllium. Beryllium is stable with 4 electrons. Whoops, that's getting a little crazy there. Let's try to redraw that. And beryllium can achieve that by forming 2 covalent bonds. Another exception is boron. Boron is stable with less than an octet of electrons. Boron is stable with 6 valence electrons, and it can achieve that by forming 3 covalent bonds. One more. Yes, I know aluminum is a metal, but aluminum has a relatively high electronegativity, and it can and does sometimes form covalent bonds with nonmetal atoms. And when aluminum forms a molecule, when it's the central atom, it is stable with less than 8 valence electrons. It is stable with 6 valence electrons. Again, like boron, which can be achieved by forming 3 covalent bonds with other atoms. So let's take a look at some examples. Draw small and leave a little space around the Lewis structures. We're going to be filling out some additional information. You have the bottom of that page and then the top of the next page. So again, draw really small. We're going to do probably 15 or so of these Lewis structures. All right, so I'm going to walk you through a couple, and then I'll give you some to do on your own. First one, go ahead and draw the Lewis structure for carbon tetrachloride. So our first step is to count up the valence electrons. So carbon has 4 valence electrons. Chlorine has 7. Each chlorine has 7 valence electrons. So 7 times 4 is 28, plus 4 more is 32 valence electrons. All right, next step is to draw our skeletal structure. The central atom is usually the first one listed in the formula. It's always the one that there's just one of. And if carbon is present in the molecule or ion, carbon is the central atom. Next, we're going to show the attached atoms. So we're going to initially space them out as much as you can from one another. So we have 4 atoms bonded to the central atom. Let's scooch this down just a little bit. So I'm going to show those. Again, a line represents a shared pair of electrons or a covalent bond. So we have 4 chlorines bonded to the central atom. Here's where my rules or steps deviate a little bit from the notes. So after you draw the skeletal structure, the next step is to subtract the number of electrons involved in bonding from the total. So according to our skeletal structure, we have 4 covalent bonds. A covalent bond consists of a shared pair of electrons. So each bond is 2 electrons. So we're going to subtract 8 from the total, which gives us 24 what I call leftover electrons. Next step is to distribute those electrons to the bonded atoms. As of right now, how many electrons does each chlorine have? Go ahead and answer that. Each chlorine is sharing a pair of electrons with carbon, so each chlorine has 2 electrons. So how many more electrons does chlorine need to be stable? It needs 6 more. As it says in the notes, complete the octet. So we're going to put 6 electrons represented as dots around each of the chlorines. So those are known as lone pairs of electrons, electrons that are not involved in bonding, electrons that chlorine is not sharing with carbon, but electrons that belong just to chlorine. So that was 24 when we complete the octet for each of the bonded atoms, and then we have no more additional electrons. Oh, something that was skipped in the notes when we want to add this. Last step in drawing the Lewis structure for a molecule is to check for octet rule. Make sure each atom satisfies the octet rule. Now, when you put 6 electrons around each of the bonded atoms, we know they're good. So when I say check for octet rule, I mean check the central atom. Make sure the central atom has an octet. We have 2, 4, 6, 8 electrons. That means each atom in this molecule satisfies the octet rule. And here is our completed Lewis structure for carbon tetrachloride. All right, let's take a look at the next one. Draw a Lewis structure for nitrogen trifluoride. Again, first step is to count up the total number of valence electrons. Nitrogen has 5 valence electrons. Each fluorine has 7, so 7 times 3, that's 21, plus 5 more, that's 26 valence electrons. Next step is to draw the skeletal structure. The central atom is nitrogen. We have 3 atoms bonded to the central atom, so initially I'm going to show those equally spaced apart from one another. Next step, subtract the number of electrons involved in bonding from the total. So we have 3 covalent bonds here in our skeletal structure, 2 electrons per bond. So we're going to subtract 6 from the total. We have 20 leftover electrons. Next step is to distribute those electrons to the bonded atoms first. So let's put 6 on each of the bonded atoms. And how many was that? 6 times 3, that's 18. All right, we still have 2 leftover electrons. If after placing the electrons, the lone pairs of electrons on the bonded atoms, if you still have additional electrons, they're going to go on the central atom in pairs. So don't do something like this. We don't want that. So put them in pairs together. Now, this is an okay way of drawing the Lewis structure for this molecule, but this is not the best way. So the best way would be something like this. Oops, we're having a problem again with the pen. Let's see if we can fix that. Let's try again. All right. So both Lewis structures are perfectly fine. This bottom one here, though, is a better way of drawing the Lewis structure. I'll explain why that is later. All right, go ahead and try this one on your own. Draw the Lewis structure for H2SE. Go ahead and pause the video now. Structure for H2SE, probably not the best way to draw this Lewis structure. So perhaps a better way would be like this. And again, don't worry about why just yet. I'll explain why later that this bottom Lewis structure is better than the top one. All right, let's go ahead and try another. Go ahead and draw the Lewis structure for, let me give you a few to work on. F2, O2, and N2. So go ahead and pause the video, draw a Lewis structure for all three of those molecules. These are a little bit different. We don't have a central atom since these molecules are made of just two total atoms. So we'll show them bonded to each other. We'll start with fluorine, 14 valence electrons, minus the 2 electrons that make up this covalent bond, gives us 12 leftovers, 6 electrons on each of the bonded atoms. Make sure both of those atoms satisfy the octet rule, and they do. Oxygen, 12 valence electrons, minus the 2 for that covalent bond. We have 10 leftovers. You can distribute them always in pairs, so either 6 and 4 or 4 and 6. Again, make sure both atoms satisfy the octet rule, which they do not. So the left oxygen does, but the right oxygen does not. So if one of your atoms does not satisfy the octet rule, look to make a double bond. If that doesn't work, then make a triple bond. So we're going to make a double bond here. So how we do that is we take a lone pair of electrons off of one of the oxygens. Doesn't matter which one we take the lone pair off of. Yes, it does. So we're going to take them off of that oxygen, and we're going to turn that lone pair of electrons into a bonding pair of electrons. So those two lines there represent a double bond, and now both oxygens satisfy the octet rule. We see something similar with nitrogen. Neither nitrogen satisfies the octet rule. So I'm going to make a double bond. So take off that lone pair of electrons and put that there. That's better. The right nitrogen is good, but the left nitrogen has just 6 valence electrons. So take off another lone pair of electrons, this time from the other nitrogen. And this time those two nitrogens we see share 3 pairs of electrons. This is called a triple covalent bond. So single bond between 2 fluorines, double bond between 2 oxygens, triple bond between 2 nitrogens. Let's try some more. Go ahead and draw the Lewis structure for boron trifluoride. Pause the video now, please. Is a double bond between boron and fluorine? If so, that is incorrect. If it was something other than boron or one of the other exceptions to the octet rule, then yes, you would make a double bond. But boron is stable with less than an octet. It's stable with 6 valence electrons, which again we can see can be achieved by forming 3 covalent bonds. So this is the correct Lewis structure for BF3. Here's another one. It is okay sometimes for atoms to have less than an octet. I gave you those exceptions. Likewise, it is okay for atoms sometimes to have more than an octet. So selenium is going to exceed the octet rule. All 6 of those chlorines are bonded to selenium. Go ahead and draw a Lewis structure for this molecule. Pause the video now. So this molecule has 48 valence electrons, 48 minus 12 for these 6 covalent bonds, 36 leftovers. Distribute the leftover electrons to each of the bonded atoms. And that is all of our electrons. All right, similarly, go ahead and try this one. Draw a Lewis structure for PF5. Go ahead and pause the video now. And we have 42 valence electrons minus, is it 42? So each fluorine has 7. 7 times 5 is 35, plus 5 more is 40. Is that right? Did I do my math right here? So subtract 10 electrons from the total. 10 electrons involved in bonding. You have 30 leftover electrons. Distribute those to the 5 bonded atoms, and we have no more additional electrons. All right, let's try another one. Structure for this polyatomic ion. Notice it has a positive charge. Look back in your notes and see what to do with that positive charge. Everything else is the same. We have one additional step at the end that I'll show you. So go ahead and draw a Lewis structure for this. Pause the video now. So make sure you're checking for octet rule every time. I've kind of been skipping over that. So each atom needs to satisfy the octet rule. Here, everything is good. Last step in drawing the Lewis structure for a polyatomic ion is to put that polyatomic ion in brackets. So the whole thing goes in brackets. And then I'll squeeze that in there. The charge goes, here, let's get rid of all this work here. And then the charge will go outside of the bracket. So additional step if the substance you're drawing the Lewis structure for is a polyatomic ion. All right, next, draw a Lewis structure for this, SO3. What is this called? This is not sulfite. This does not have a charge. This is sulfur trioxide. Go ahead and pause the video now, please. Here's the Lewis structure for sulfur trioxide. This is not entirely correct. We see that sulfur does not satisfy the octet rule, and it is not one of the exceptions, so it does need to satisfy the octet rule. So we're going to look to make a double bond. Question is, where do we make the double bond? Here, here, or here? In this case, it doesn't matter. So we're going to take off a lone pair of electrons from one of the oxygens, doesn't really matter, and turn that into a shared pair of electrons. And now both sulfur and that oxygen satisfy the octet rule. We're all good here. All right, I'm going to break this video up into, or this lesson rather, up into 2 videos. We got quite a bit left to go, so we'll continue in the next video with some more Lewis structures. We have 1, 2, 3, 4, 5, 6 more, and then we'll move on to molecular geometries. All right, stay tuned.